Okay. Yeah. Okay, cool. So I think we're good to go. So yeah, thank you so much. Okay. Alrighty, so hopefully everyone here has picked up your exam. If you're at home watching this recording, I will not bring them to lecture with me on Friday, but I will have them at my help room hours right after the Friday lecture, so you can swing by and pick them up then. After that, I'll parcel them back out to your recitation TAs, and you can get them in recitation next week. Okay, so a few administrative things about this exam. So the average was 76.4, so I usually shoot for about 75. So I ended up not needing to curve this one at all. The max, you might notice that I messed up the points counting because I was tweaking some of the problems and forgot that one of them on the last page should have been 10 and one should have been 16, and I made them both 16. So there's up to 106 points possible, but I am still making it out of 100. So 6 free extra credit points for anyone who does really well on the exam. So we did actually have one perfect score, so excellent job, that person. We also had some scores towards the lower end of the range. If that's you, I guess like, so, all right, so I guess like this is the time for my first post-exam pep talk. If you didn't do as well as you would have liked to do, don't panic necessarily, because the way the grading works, if you'll remember from the syllabus, I do allow you to use either your overall course total or just your final exam grade by itself. But if you're having a rough time with the material on exam 1, you need to reevaluate like what you're doing to actually study. So if what you're doing now isn't working for you, play around and try some other study techniques or habits. Find something that maybe works better for you. So there's a bunch of resources available to you. I guess for starters, working as many problems as you can is kind of the best way to get good at OChem. But if you sit down and you look at the problem and you have no idea what you're even doing to start it, getting some assistance is crucial to fixing that. So the help room staffed about half the time during the week. The schedule's on the website and also outside the help room. If you don't know where the help room is, it's just around the corner from the organic labs. Or if you go to help room and it's busy and you feel like you would need some more one-on-one time with someone, there's a tutor list on the chemistry department website. I have it linked from the OrgChem website as well. If you go to like lecture courses, at the bottom of that drop down, there's a link to the department tutor list. That's not like officially like sponsored by the department. The department just puts together a list of people who are interested in offering like private tutoring one-on-one or like in a small group or whatever. I think the going rate's like $25-30 an hour, last I heard, but pretty much like there's just a bunch of contact info on there. So feel free to like email a few people who are offering OChem, get in touch, like maybe meet up once and see if they work for you. That's there as another option. Aside from that, like I also have help room hours, feel free to drop in. But pretty much just like don't go into this with very little practice on your end and expect that you're going to immediately understand the material just because it made sense in lecture. Like you gotta practice it if you want to get good at it. So that might be something to change. And then I guess as far as like how to read the material, I guess like, not to toot my own horn, but the lecture notes are kind of like what I emphasize more out of the chapters. So I know like some people go into this, they're like, I can read a novel, I should be able to sit down and read the entire textbook chapter start to finish. That might work for you, but it also is kind of like drinking from a fire hose. There's a lot of information in there. Maybe start with the chapter notes, and then that'll give you like a framework for what's going on in the chapter and what the key points are. And then you can go back, read the textbook chapter and fill in the gaps or like build some more understanding like into the framework that you already have. Okay, so a few different strategies. If you want to talk some more about like maybe like what am I doing wrong or how can I improve my studying, drop by office hours and we can look at it. But you know, you're certainly not at an unsalvageable situation if you didn't do as well as you wanted to do. So as long as you like don't keep beating your head against the wall and try something new, then you should be okay, hopefully. Okay, so With that said, I'm actually going to spend today going over the exam. So I posted the key on the website. And as a reminder, my regrade policy, if you look at your exam and you see that it's graded not in accordance in some way with the way that the key is on the website, you can submit a regrade request, and the deadline for that is 1 week. So by 9 a.m. next Wednesday. So the way the regrade request thing works is you got to staple a sheet of paper on the front of your exam saying, please regrade problem such and such. I feel it was graded unfairly because blah, blah, blah. Try to keep it brief. I don't want like a 2-page letter about how I've done you wrong, which I have received longer than that before. But pretty much just like, you know, this is not graded in accordance with the key, or maybe like I feel my answer is also correct even if it's different from the key. And then, like, I can't guarantee you'll get points back, of course, but I will at least look at it and write you a note saying, actually, this is wrong because blah, 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 or you're totally right. Sorry for not catching that, or whatever. Okay. So questions about that? Okay, yeah. Say again? I guess hypothetically, but that's never actually happened. I don't regrade the whole exam because I don't have time for that. I just look at the problems that you submit or regrade on. So I guess like if, you know, if something was added up wonky and then I realized that, yeah, you earned points back on this part, but also the grader added it wrong. But I'm not going to like regrade the whole thing. So, okay. So that said, like, do try to do this in good faith. Please don't try to just like snag every point that you have the ghost of a chance on. Just do it if you think like you honestly did get a right answer. Okay. So my plan for today is to go over the key. All right. So some of the parts of this exam, like people did a lot better on average with than others. I'm going to kind of go through in order, but I might go a little bit faster on the parts that everyone more or less nailed. Okay. So draw products based on the arrow pushing shown. Okay. Okay, so for this stuff, it really, really helps to remember what the 3 legal moves are, because you can go lone pair to bond, bond to lone pair, or bond to bond on the same atom. So for this one, we showed an arrow of the lone pair on carbon going for the proton and kicking over onto the oxygen. So that means that these electrons in the OH bond are becoming a lone pair on oxygen. So the OH bond should be broken. And I guess if you want to fill in the lone pairs before and after, you can do that, but you didn't have to. Okay, so now we have 1 more lone pair on oxygen than we did before. Also a negative charge there. And we have a bond from this H onto this carbon. So we're taking a lone pair on carbon is making a new bond between carbon and the H, is how that works. So H connected to H2C, or if you want, you can show it like down here. As long as you've got the connectivity right, it doesn't matter exactly how you show it. And then the rest of the molecule didn't actually change at all. There's no arrows going on with the nitrogens. So that goes like that. Okay. Questions about that one? Okay, cool. B is a little bit trickier. All of these, by the way, are actually steps of mechanisms that we'll see in future, sometimes like towards the end of OChem 2. When we see it then, I'll expect you to actually like just be given this and be able to draw the mechanism and the products. But if I give you the starting material and the arrows, then you should be able to figure out the products based on what we already know. Okay, so the arrows for this one, that comes in and attacks here. That kicks up. So most of this molecule is going to be unchanged. So that doesn't have anything going on, neither does that. I'm taking one of the lone pairs on this oxygen, and I'm using that lone pair to bond move to make a new oxygen to carbon bond. So I have an attachment here that I've just formed with OCH3. Fluorine hasn't gone anywhere. Nothing's happening with this bond, so it's still attached. Okay, and then this pi bond here, these electrons are going out of the CC bond here, and they're becoming a lone pair on this carbon. So I now have lone pair on that carbon. And then just to double check, this oxygen had a negative charge. It gave up electrons. It should end up neutral. You can also double check that by actually calculating the formal charge. This carbon here is sort of at the end of the arrow chain. It has electrons incoming, and it didn't lose anything by doing that, so it should end up with a negative charge, which you can also verify by checking its formal charge as well. Okay, questions about that one? All right, cool. Alrighty, C. Okay, so here are the arrows. We have this pi bond, goes out and attacks bromine, kicks out that bromine, and also these electrons come back here. So this one we have multiple things going on at once. All right, so we still have this carbon framework mostly intact. We've lost the pi bond. These electrons are going out of the CC bond, and they're instead going to form a new C to bromine bond here. And then meanwhile, these electrons on the bromine are also going from a lone pair to form a new CBr bond over here. And at the same time, this bromine on the right is getting kicked out with a negative charge. Okay, so we know this bromine has a negative charge because it has electrons coming at it and it doesn't lose any. Meanwhile, this bromine has one arrow coming in towards it, so it's gaining some electrons, and it has two arrows going away from it. It should end up shorter on electrons than it was before. It should have a positive charge. And you can again verify that if you go through and calculate formal charge on here. Bromine has one less electron than it would really like to have, according to the periodic table. Okay, question, yeah?
How do you determine when the pi bond that's breaking, that those electrons are going to form a bond instead of just transferring their lone pairs onto the bond?
Because a lone pair to lone pair is not a legal move. Yep, so it's got to be like they stay on the same atom.
To an atom?
Sorry?
A bond to an atom. The bond going into the lone pair.
Right, so these electrons are in the bond and they go and form a new bond onto the bromine. Sorry, you're asking about if we go bond to lone pair on carbon, you mean?
No, I'm saying, how do you know that bond does not go to bromine to create a lone pair?
Because it's got to be, so lone pair to bond has to be involving the same atom. So I could have gone bond to lone pair, I mean. Has to be involving the same atom. So I could have gone bonds to a lone pair on carbon. That would be a legal move, but bonds to a lone pair someone else is not a legal move. So it's got to stay on the same atom. Okay. Okay, so this last one, we have pi bonds doing stuff. We've got this one kicks over to here, this one kicks down to here, and this one goes up to here. So what I'm doing is taking, and I'm actually going to shade them in just to make it a little bit easier to see here. These three pi bonds, are all getting turned into something else. This one is going to form a new bond. I'm going to draw a little dotted line here from this carbon onto this carbon. So I'm going bond between two atoms into bond to this atom becomes a different bond to this atom over here. The sigma bonds here, here, and here all stay the same. But this pi bond here, again, I'm going bond on this carbon becomes different bond on this carbon. I'm flipping this pi bond over. And then this pi bond is going from being a bond to this atom to a different bond to this atom. So this is another bond-to-bond move. So I'm making a bond from here down to here. And these two keep two of their bonds together. Okay, so what I'm getting is 2 new sigma bonds out of it and 1 new pi bond where I didn't before, and I'm spending 3 pi bonds to do that if you want to keep track of it that way. Okay, so that's definitely the trickiest of the 4, but as long as you sort of follow, like, I'm taking these electrons out of a bond that involves this atom and I'm making a new bond that involves that atom, you can sort of follow it that way. Okay, other questions about this one? Yeah.
I have a question about part C.
Uh-huh.
How do you know that it would make that triangular structure instead of just a double bond?
Good question. So I guess if you're trying to make a double bond from this bromine, and it might actually help if I also explicitly write in the hydrogen there too, because if I do that, then something should immediately jump out as not okay about that structure. You're violating the octet rule on here. Yeah.
On that same note, is there ever a situation where those circular arrows mean just the bromine makes a single bond and then the double bond gets replaced between like where it was, or is that the same reason?
So I think because you've got like 1 arrow forming a CBr bond here and another forming a CBr bond over here, it's got to make 2 total bonds just based on the arrow pushing that we've shown. What you're asking about like could be sort of a valid mechanism. It just isn't the one that I happen to draw the arrows for here. Yeah. Okay. Yeah.
For part B, the top bond, how do you know that that's a bond and not a bond to lone pair?
So I guess for one thing, I'm showing it going to the space between the atoms, which is usually kind of an indicator that I'm going bond to bond here. And for another, like if I did go, say, bond to lone pair on this carbon, then, so let me actually draw that out too as another option. So if I had done that, I would end up with a minus charge there and a plus charge there, just based on like I have electrons here that are getting spent on the carbon instead of a bond between them, and then everything else would still be the same. And so even if you're not sure like exactly how to interpret the arrow, you could get to this point and realize like, hold on, I have a lone pair here. Why wouldn't I just like get both things like charges neutralized out and also fill the octet of both by making a double bond there? Okay. Questions about that one? Okay, cool. So I'm going to go on to 2 here. Okay, so show all major resonance forms for this molecule. And note that in the problem, I didn't actually request arrow pushing, so you can show it if you want, but we didn't grade on it. But it is still useful for like helping yourself figure it out. Oops. Okay. So the trick to this one is look for those 3 atom subunits, flip the ends around. Pretty much every structure that you can draw in resonance for this thing is going to involve that 3 atom pattern of charge at one end, pi bond at the other end. So Here's one. And here's another. And then I'm just going to keep looking for that pattern as I travel around the molecule. Quick question, can I ever get the minus charge out to this part of the molecule? Correct, I cannot because I don't have any pi bonds that will let me travel out there. So this one you can show resonance of like the benzene doing stuff internally, but really we're just kind of focusing on the minus charge moving around. If you did show this stuff, that's fine, but really we were just assigning points for the negative charge. Okay. Okay, so again, we start with this 3-atom unit, flip that around, and then gets us to here. Another 3-atom unit. Gets us to here. And then from here we actually have two options of where we could go because we could look for a 3-atom unit out this way or inside the ring. I'm going to show it going out this way first. So again, kick in, bump over. So there. That's not actually correct. Okay. Sorry, I dropped some double bonds along the way. There, okay. There we go. So that's one option. Or I could have gone out the other direction. So maybe if you want, you can show resonance to get right back where you were, dump the negative charge onto here, or since we know we're going out to like the far right end of the molecule anyway, I can use arrows to get from any one resonance form to any other resonance form. It might just take more arrows. Okay. So that's where that gets me. Okay, so all of these forms are going to be pretty similar in energy. All except one have a minus charge on a carbon, but one of them has a minus charge on an oxygen. And all else being equal, everything has a full octet the whole time. So the negative charge on oxygen is going to be the better location for it. So this is going to be the most stable. Okay, questions about that? Okay, cool. Yeah.
How come it's not, I guess, major resonance to move the double bond left?
So, sorry, let me move the camera real quick so I can draw it. So trying to move the double bond left, the problem is that and I'm going to redraw the starting material here. Okay, so I think I have too many carbons there. Actually, there you go. Okay. So the problem is I don't have that 3-atom subunit. I literally can't kick the oxygen, kick the lone pairs over to here because all the carbons here are like they have two H's on them. There's nothing I could do with that without breaking a CH bond.
That makes sense.
Yeah. So I pretty much like have to deal with just lone pairs and pi bonds if I want to shuffle stuff around.
Sounds good.
Okay. So other questions about resonance? Okay, cool. How much time I got? Like 10 minutes? Okay. So I might skip ahead a little bit. Maybe I'll just do like one part of each of the following problems so that we can get a little bit of coverage. I guess for problem number 3, between A, B, and C, show of hands, how many people want to look at A? How many people want to look at B? And how many people want to look at C? Okay, B it is. Okay, so 3B. Okay, so draw curved arrows to indicate electron movement. So this thing is symmetrical. We could go for either of the high electron density areas, either of the N minus, and attack that proton. May as well just show it from the one that's just closer to it already. And then we attack the proton, which means the proton has to drop its bond out the back onto the oxygen, which gets us to this plus this. Okay, so that's the arrow pushing. Any questions about that part? Okay, arrow pushing for proton transfer is pretty straightforward. Then what we got to do is go check out the pKa table and figure out how good are each of the acids that are involved here. All right, so the acid here is listed on the table as CH3COOH. That's the formula of this. It's a carboxylic acid, by the way. pK is 4.7. The acid here is formula HN3. So that's going to be also 4.7. So I picked these two because they happen to be the only two in the table that I give you with the same pKa value. So products or reactants, which one's going to be more favored? Neither. Yep, it's a trick question. I guess I did list neither as an option in the problem too. So, or you could say like equally favored is another way to describe that. Okay, any questions about that one? Okay, cool. Okay, so 4, I feel like people generally did pretty well on. I guess checking for sp2 and sp3 hybridized carbons, if you had a hard time with that, that might be something to go through and double check. But I think I might skip ahead to do a naming one in the time that we have left. Okay, so out of problem 5, the naming thing, show of hands between A, B, and C, how many people would like to cover A, B, okay, and C? Okay, cool. I think C had the most people. Okay, so 2-cyclobutyl propane. Okay. So, what the structure must have looked like if someone incorrectly named it this. So we got propane here, 3 carbons, and a 2-cyclobutyl hanging off of it. Okay, so looking at this though, we know that the ring actually has more carbons than the chain coming off of it. So the ring should be the parent. So really we got to name this as cyclobutane with a thing attached to it. Question? Oh, well, so this line here, you mean? So that's actually like saying that these two things are bonded together. So like this person interpreted this as like it's a propane molecule with a cyclobutane substituent on it, or cyclobutyl substituent on it. But we're actually going to interpret it the other way. Is that what you're asking? Or okay, cool. Okay, so our parent chain is actually going to be this cyclobutane here. And what's the name of this group that we got dangling off of it? Isopropyl, yep. So we're defaulting to assuming that's position 1 because we can start numbering anywhere. So we could call this 1 isopropyl cyclobutane. We can even drop the 1 though. So just isopropyl cyclobutane. So pretty much they almost got this correct. They just misjudged which part to be the parent and which part to be the substituent. So if you swap that, you're good. Okay. Other questions about this one? Yeah.
Why can we call that 1,1-dimethyl ethyl?
Because 1,1-dimethyl ethyl would actually be this thing. Because if you called it, so like 1, 2, there's your ethyl group, and then like 2 methyls on that gives you 4 carbons total. Yeah. But you could have called it 1-methyl ethyl. That would actually be a valid thing if you did it in parentheses properly. So, okay. Yeah.
See that as like propane comes out of second number of carbon of cyclobutane.
Because once you choose cyclobutane as the parent, which is the correct choice, you have to start numbering at the point of the first attachment. So this has to be carbon number 1. So, and then like you just say there's an isopropyl stuck on there. So, yeah. Okay. So other questions about that one? Okay, cool. How much time I got? Okay, so 5 minutes. Alrighty, I guess let's move ahead to number 6. So parts A, B, C, and D. How many people want to look at A? How many people want to look at B? How many people want to look at C? And how about D? Okay, B and C looked pretty tied, so I'll do both of them. They're pretty short. Okay, so 6B, an alkyne with formula C4H6. With 1 methylene unit. Okay, so as a reminder, I think the use of this confused a lot of people. A lot of people tried drawing methane double bonded to itself or something. As a reminder, we saw a methylene unit in our homologous series when we started introducing alkanes. Remember that methylenes or CH2 units can insert into the middle of a chain and lengthen it out by 1 carbon. So we want an alkyne with 1 methylene unit in it in the chain somewhere. So we know we've got to have this. Let's just throw our methylene unit in there. And then we got 1 more carbon. So CH3. And then throw an H on there. So basically it has to be a 4 carbon chain with an alkyne, which as a reminder is a triple bond. And then it's got to have a CH2 in the middle there. Okay, so questions about that? Okay. So C is a ketone with C5H8O with 1 trig planar carbon. Okay, so ketone means it's got to be this. So you can start out like assuming, okay, what if I just put it in the middle of a chain here? That is a ketone, but if you go through and count your hydrogens, you get 10 hydrogens, which is too many hydrogens. So a bunch of people tried getting around that dropping down the hydrogen count by throwing a double bond in on one side. What's the problem with that? Yeah, so now you have 2 more trigonal planar carbons in addition to the one you already have, so that's not going to work. So instead, what you can do is make some kind of a ring. So the key, I put just a 5-membered ring containing the ketone, but there's actually a bunch of different options. Like you could have done something like this would also be a valid ketone, where you've got a ring in there, something like that, so long as you have like some way of getting your hydrogen count decreased by 2. Another way of looking at this is by looking at the degrees of unsaturation. You don't have to use that, but it does make it easier if you do, just keeping track of the pairs of missing H's. Okay, questions about that one? Okay, cool. So I'm out of time. If you have any more questions, please check the key online, and then I'll have the rest of the exams in help room hours on Friday for anyone who's not here.